Welcome to Operating Systems lecture 28. Right. So last time we were discussing sleep wake up on XV6, and we said sleep wake up is actually identical to condition variables, except that we don't explicitly declare a condition variable, we just sleep on some channel, and that channel is some identifier. And earlier in condition variables you would have declared a condition variable associated with that channel. Now you don't need to declare anything separately. So that way you don't have, because a condition variable has no state, you don't need any space for the condition variable. So really this channel is nothing but an integer, right? Any 32-bit integer that can be used to indicate that I am sleeping on this channel, and then you use the same integer to indicate that I want to wake up all sleepers on this particular integer, right? So that's what it means. And we said that we looked at some examples. We said, look, there is exit and wait. We understand this exit and wait system call. In Unix, and XV6 implements the same. So parent calls wait, let's say, and if it finds a child that is currently not a zombie and running, then or active, then it sleeps on its own PID, right? So the channel is basically its own PID. And if a child calls exit thereafter, then it calls wake up on its parent's PID, and so that's how you basically ensure that you only wake up your own parents and nobody else. And we also said, instead of this convention, if I had a more general convention where instead of sleeping on my own PID, I sleep on some global identifier, that would have been also correct, provided you are enclosing the wait, enclosing the sleep inside in a loop which is checking the condition, right? So if a child calls wake up on all the parents, then all the waiting parents are going to come out of the sleep only to go back to sleep. Right. So that's okay. It's wasteful, so it's better to have as fine-grained channels as possible, and so this makes a lot of sense. It's exactly as fine-grained as you can get in this particular example, right?
Sir?
Yes.
So in the current case, when you are sleeping on your own PID and the child is waking up the parent's PID, do we need to check for the condition, because at most only one process can be woken up by a child?
Okay. All right. So the question is, in this case, if child, if I'm using this convention that a parent is waiting on its own PID and child is calling wake up on its parent's PID, do I need to enclose the sleep in a while loop? Can I just use if, so I can be sure that if a parent has woken up from sleep, then definitely one of its children is zombie, and so it can be collected, right? Well, I mean, yes, you can do such reasoning. We have seen such a thing in a single producer, single consumer case. But doing these kind of reasonings is usually error prone. As I'm going to show you next, there are other checks that you have to make, whether the process has been killed in the middle or things like that. So it's always better to put it in recheck after coming out of a wait, that whether the condition is true or not. And the overhead of rechecking is very small, anyways, right? It's just a memory operation to basically do it. Also, it's possible that so you basically said I'm going to use this convention for exit wait, but let's say completely unrelated part of the code wanted to use some other synchronization, and it also decides to sleep on the PID of some process, right? So let's say there's some synchronization going on due to some other completely unrelated part from exit wait exit, right? And so that also sleeps on PID, and so now they can sort of cross communicate, and to protect from errors because of this cross communication, you should always enclose your sleep within a while, right? If you don't, then you have to be very careful. It becomes a global invariant and nobody else should be sleeping on the PID, for example, right? Okay. All right. So today I'm going to discuss another system call called kill, right? So we have seen the kill system call in the context of Unix, where we said that you can say kill on a PID, and that will send a signal to that particular PID, to that particular process. So you can say kill PID with some signal, and that signal will be sent. XV6 doesn't implement signals, so kill PID doesn't send a signal to the PID, but just terminates that particular process. The idea is if I send kill on a process ID, then that process gets terminated. So how do you think kill can be implemented? Can I just if some process calls kill, can I just immediately acquire the ptable lock, go to its process and free all its structures? Does that make sense at all? Does that make sense? Yes? No? Why not? one process called kill PID. That process just acquires the p-table lock, goes through the proc table, finds the process with that PID, and frees all its structures. Is that okay? What if that process is currently running? Right? It's in the middle of something, and now you have just freed up all its structures. Let's say you freed up its K stack, and it was running in kernel mode. Suddenly there will be some bad things that are going to happen. It could be in the middle of some operation. It has not finished its operation, and now you free it or you completely terminate it. Firstly, it's running. So how can you just free it? If you free it, then you haven't told it to stop. You have to have some way of asking it to stop. Also, it could be in the middle of something, and you want it to come out of wherever it is, and then exit gracefully, right? And so the way you would implement this kind of a thing is that you will basically have a flag inside the proc structure called killed, right? So there's a structure called killed inside a proc, and if one process calls kill PID, then I will just iterate over the proc table, find the process, and set its killed bit to 1, right? So by default it's 0, but I'll just set it to 1. Now it is that process which will basically, if it was in the middle of something, then it will just, when it comes out of it, it's that process's responsibility to know that I have been killed, and so it should exit. Right? So if a process has been killed, it should exit, and exit will not free up its data structures either. It will be its parent who will call wait, and then that will free it up. Okay. In any case, so the point is that kill cannot be done immediately because the process may be running. So the way it's done is you just set a bit in that process's structure, and let that process run. When the process comes out of wherever it was, then it should really check whether I have been killed or not, and then it will exit. All right. So when you set proc.killed, you are accessing the shared proc structure, so you should be holding the p-table lock. All right. So you just hold you use the p-table lock to basically set this bit, but after that it's that process's responsibility to basically exit after it has checked that it has been killed. All right. Okay. Yes. Is any process allowed to kill any other process? Well, if in Unix, if the processes belong to the same user, then a user is allowed to kill its own process basically, but one user is not allowed to kill another user's process. Also, modern operating systems like Linux have a concept of a root user, which we all know that the root user is super user. So root user can kill any other user's process, for example. So you can have this access control mechanisms, but in XV6 you just have one user, so any process can kill any other process. All right. So I'm saying that one process just sets the killed bit of the other process, and I now expect that process to basically exit, right? So what if it doesn't exit? What if it's a malicious process? How do I make sure that that process will definitely exit in some bounded amount of time? So firstly, you don't trust the process's user space, but you definitely trust the process's kernel space, right? Anytime the process is executing in the kernel mode, it's your code that's running, right? It's not the user's code that's running, it's your code that's running. So you always trust the process's kernel space, right? Because process in the kernel space is just a kernel thread, and you completely trust that code. So anytime the process is executing in the kernel, you can be sure, and because you have written the kernel code, you can be sure that it will call exit whenever kill bit is set. Now you can say that what if the process remains in the user mode and never comes in the kernel mode? But that's not going to happen because you have a timer interrupt that makes sure that every process periodically comes in the kernel mode. So whenever it comes in the kernel mode next, it is going to check whether something, whether it needs to exit or not. Okay. So once again, this orchestration has been done by the kernel programmer. Okay. All right. Also, let's say I set the killed bit of a process, and it was sleeping when it was killed. Right. So let's take a few cases. Let's say this process was running when it was killed, and let's say it was running in user space when it was killed. No problem. Eventually it will come to the kernel space either because it made a system call or because of the timer interrupt, and as soon as it comes into the kernel space, it should check whether I have been killed or not, and if it has been killed, right at the entry you should put a check that if I have been killed, then I should exit. And that's a very safe place to exit, because you are not in the middle of any kernel operation. You have just come from user to kernel, and you can just ask him to exit right there. So this is easy. Let's say I was running in kernel mode. Right? So I'm running in kernel mode. I could be in the middle of doing something. Of course, I'm using the K stack and all that. And so basically I should wait for the kernel to finish whatever it's doing and then come back. Quite likely, if it's running in kernel mode, either it will return back to the user mode eventually. So that may be a nice place to check the kill flag. So right just before re-entering the user space, you can check the kill flag and call exit before it re-enters the user space. Right? That's one thing. If it's running in kernel mode but it's not going to re-enter the user space, it's possible that the only other possibility is that it's going to sleep, right? Or it's going to do something else. So all these places where it could be going to sleep, for example, before you do that, you should check that it's killed, and you should check it all these sort of boundaries where you're not in the middle of something. So at any place where you are sure that all the kernel data structures are consistent, at that point you can put this check that if I am being killed, then I should exit. Okay. All right. Now let's say I was sleeping. Right. So sleeping, of course, can only happen in kernel mode, right? It doesn't make sense that a process is sleeping in kernel mode, in user mode. If it's in the user mode, it must be running something. If it wants to sleep, it will come to the kernel mode, and then it will call the sleep function to basically sleep. So let's say it was sleeping in the kernel, and you basically said proc.killed is equal to 0. What will happen? Is equal to 1. What will happen? The process was sleeping, it will never get scheduled, and so it will not get so the killed is not going to have any effect. It's just going to sleep forever, maybe. So not only do you set proc.killed is equal to 1, you also say if it was sleeping, then mark it as runnable. Right? So here's something sort of dangerous looking. I'm saying any process who is sleeping, if it has been killed, just mark it runnable. All right? Irrespective of what was the condition on which it was sleeping, what was the channel it was sleeping on, doesn't matter. Just mark it as runnable. It will get scheduled eventually, and when it gets scheduled, it will get to run. Okay. Now it's the responsibility of the programmer to ensure that whenever a process comes out of the sleep, it also checks whether the killed flag has been set or not, right? And if so, then it should exit. Okay. So once again, it's a kernel programmer who is making sure that firstly you need to do this, because otherwise a sleeping process will never get killed, and if you need to do this, you may be violating some invariance, because after all the process went to sleep on some condition, and that condition has not yet become true, but you've still made it runnable, and so it will come back and it will basically, but before you start doing anything, you should probably check whether it's been killed, and if so, it should exit. All right.
So but if it is sleeping, we can assume that after some time it may wake up and then we can exit.
Okay, if it is sleeping, I can assume that after some time it may wake up and then it can exit. Well, I mean, so let me think of an example where it may be sleeping and it may not wake up. So, well, let's see. So let's say I was a parent and I wanted to wait on my child to exit, right? And so my child is going to run for a long time, and somebody wants to kill me. Right? So should I wait for the child to finish its execution before the parent gets killed? Maybe not, right? So you want to basically kill it right then. There should be some bound on the time it takes between the kill operation and the actual act of getting killed. Right? Otherwise, you have killed it, but it still appears on your process table. That's not a good idea. Okay. All right. So, okay, and it may not be always necessary that when you come out of sleep, you always check the killed and you exit. It really depends on the semantics under which you are sleeping, and I'm going to show you a couple of examples to show when you need to exit on being killed and when you don't need to exit on being killed. All right, so let's just look at the code. So this is sheet 31. And this is the kill function. All right. So the first thing you do is acquire ptable lock, right? Then you check, you iterate over the ptable, find a process whose PID is equal to the argument, set its killed value to 1. If it is sleeping, mark it runnable, release the ptable lock, and return. All right, that's it. Okay. So now let's see where the killed is being used. So this is sheet 26. Sorry, not 31. Sheet 26. All right. Let's look at sheet 31, where the killed flag is being checked. So this is the trap function. Recall that the trap function gets called on every trap. A trap is both a system call or an external interrupt like a timer interrupt, or any exception like a page fault, right? So all these are basically traps, and so the trap function gets called. Recall that the all traps function, all traps assembly code used to call the trap function, so the trap function gets called every time. And you can see here that at entry you are checking if proc.killed exit, right? Similarly, after that you basically execute the system call, and on exit you are saying if proc.killed then exit, right? And so you will see similar sort of peppering of this code if proc.killed exit at other places in the code. For example, here's another example. Let's say if proc and proc.killed and I was executing in user mode, then exit, right? So for example, there was a timer interrupt while I was executing in the user mode, and the process has been killed since the in the past, then exit. Similarly, you'll see something somewhere here. Right. So these are the places. Notice that he's basically identified some safe places where you should exit. You should check and exit. Also, he has made sure that there is a bounded amount of time within which it will exit. Okay. All right. Now let's look at the wait and exit code that we were looking at last time, right, just to complete the discussion. So here's, let's say, the wait code, right? This is sheet 24. I'm looking at the wait code, and recall that I was acquiring the ptable lock, iterating over the ptable, and and if I find that there was some child, if this process has a child that is not yet a zombie, then I will go to sleep, right? So let's say I was sleeping. So let's say this process was sleeping here, and it's really waiting for one of its children to exit. Now somebody calls kill on this particular PID. So what will happen? It will be marked runnable. It will come out of sleep immediately, even though none of its children have actually become zombie yet. It will come out of the sleep. It will. The nice thing now is, I'll go back and check the condition again, right? So here's an example where you actually, even though you have chosen the channel correctly, you had to check the condition again because there are other reasons why you could have woken up, right? So you check the condition again, and once again you find that there's nothing that has yet become a zombie. None of my children have become a zombie. I come here, but this time I find that I've been killed, and so I'll release the ptable lock and return -1, and return -1 will eventually go back to system call exit, and there you're going to check whether it has been killed. Then it's going to call actually exit, right? So in this loop of checking, here's an example where you basically if somebody has been woken up from a sleeping state unceremoniously, not correctly, then you will basically the programmer is handling it correctly, and this is very important to handle it correctly. All right. Okay. All right. Okay. Now let's look at another example of how wait and notify is used, and I'm going to look at the IDE device driver, the disk device driver. So IDE disk driver, device driver. As we all know, a computer system is made of a CPU, main memory, and a lot of devices, right? And one of these devices is the disk, hard disk, magnetic disk, let's say. And IDE is just one interface, one standard interface to communicate with the disk. So it's a standard. The IDE device manufacturer will conform to that standard, and the operating system developer will also conform to the standard, and so they can talk to each other. All right. So let's see what happens. Basically, there are multiple processes, right? And they may be calling read or write system calls. And eventually, the file descriptors of these read and write system calls may be pointing to the disk, right? So when they make a system call, they become kernel threads, and these kernel threads will try to access the disk and read or write data from the disk. So what sits in the middle is this IDE driver, right? On the XV6 code, this function is called IDE RW, IDE read write, right? There are multiple threads who are coming inside this, trying to access the disk, and they all go through this device driver to be able to access the disk. Also, because the disk is really slow, as we already know, what we also keep here is what's called a cache, right? So if you read something from the disk, you basically store it, keep it in the cache, so that if somebody else wants to access it, then it just gets satisfied from the cache. And notice that this cache is a shared cache. It's shared across all the processes, right? So if one process tries to read something, then it comes into the cache, and another process tries to read the same thing, then it doesn't need the disk access. You save disk accesses because of a shared cache. And so because it has to be a shared cache, this cache has to be implemented inside the kernel, right? If it was not a shared cache, you could have implemented the cache at user space also. I mean, it doesn't matter, right? But because it's a shared cache, it has to be implemented in the kernel, and almost every kernel has it, and this is called the buffer cache. That's a common name for it, right? So buffer cache has many buffers, and so it just reads data from the disk into the buffer, and all subsequent requests are checked against the buffer cache. If you can satisfy it from the cache, then you just return it from the buffer cache. Otherwise, you go to IDE RW to reach the disk. All right. Okay. All right. So firstly, there's just one disk, and there are multiple logical processes, right, and multiple threads. The threads could be logical threads, or there could be logical concurrency or physical concurrency. In either case, you need to provide mutual exclusion on your accesses to disk. So only one thread should be accessing the disk at any time, right? So that's needed. So basically what you do inside IDE RW, you have some lock. So on XV6 you have an IDE lock. So every thread before it tries to access the disk must acquire the lock and then access the disk. So that makes sure that only one thread is actually controlling the disk at any time. So one thread comes in, talks to the disk, gets its data or writes the data, reads or writes the data, goes out, then another thread comes in, and so on. So it's completely sequential in that sense. Also, as we know that a disk is really slow, right? So it's quite likely that there are lots of threads that are waiting for the disk to be available. If there's a very slow thing, then a queue will usually get built up in front of that slow resource, right? And so the best thing to do would be to sleep as opposed to spin, right? Because the disk is basically milliseconds, and you don't want to spin for milliseconds long, so you would probably want to sleep. So you will basically sleep on something, and so when the disk actually gets done, then you will wake up the corresponding process, right? Also, device drivers are basically written in one of the two ways. One is called polling, and the other is called interrupt based, right? So what this means is, let's say I request the disk to do something. Let's say I ask the disk to say to read some data. I want to read the sector number 10. Now I can keep asking the disk. So the disk is going to take some time, and so I can keep asking the disk, are you ready, are you ready, are you ready? All right. So that's called polling, right? You keep polling the disk for the data, right? So you basically just keep checking at some periodic interval, whatever you think is valid, you just keep polling the disk at periodic intervals, and as soon as you get the data, you give it back, right. Polling is alright, so that's one way to do it. The other way to do it is interrupt based, where you ask the disk to do something and then you go to sleep, right. And now the disk has been configured to generate an interrupt whenever it finishes. So I don't need to continuously keep asking it, it will call me back using an interrupt. So it will generate the interrupt, and the interrupt handler, when the interrupt gets generated, I can check whether my job has been completed, and if so, I will take it, right. So there are two ways to deal with devices in general, polling and interrupt based. Slow devices are better dealt with in interrupt based manner. Faster devices are better dealt with in polling based manner, right. So the other thing is this IDE device has to be interrupt based, right. So what's going to happen is that a thread is going to take the lock, it's going to enqueue its request into a list, into a queue, and then it's going to go to sleep. Whenever the device finishes, it's going to generate an interrupt, and the interrupt handler is going to call wake up, right, so that that process can actually continue. So whoever job has been done, that process will be called, you will basically wake up that particular process, all right. Okay. All right. So the way it works on XV6 is basically that you have a queue which it calls IDE queue, and this has all the buffers that are waiting for disk access. Each and so there are multiple threads that try to add to this IDE queue. So you basically take so protected by IDE lock. So if there are multiple threads who want to access the disk, they are actually trying to, they first contend on IDE queue. So they contend on IDE queue and enqueue their request on this IDE queue, and this IDE queue is processed in FIFO order by the disk, right. Now the disk, so now the driver basically picks up one request from here and asks the disk to do it. The disk generates an interrupt when it's done, and it basically, so whoever was the process that requested this particular thing, that particular process is woken up, and that process can now go on its way. So a process enqueues its request on the IDE queue and goes to sleep, right. So enqueue and sleep, and when the IDE device takes one request at a time, and when it's done, then it wakes up the sleeping process, corresponding sleeping process, right. So let's look at this code. This is IDE RW on sheet 39. Okay, so this is the function IDE RW. It takes an argument buffer, which is some pointer into your buffer cache, and the semantics are that if the buffer is the struct buff has a field called flags, and if the be dirty field is set in the flags, then you should treat it as a write request. So you want to write this buffer to the disk. Else if be valid is not set, then read the buffer. So whether it's a write request or a read request is encoded within the buffer in its flags. Whether if it's valid, if it's not valid, then it's a read request. If it's dirty, then it's a write request. All right. So here are some debugging aids. Firstly, all right. So we can ignore this for a minute, and we'd say either it should be valid or it should be dirty. Right? It cannot be that it's neither. Either it should be not valid or it should be dirty, basically. Okay, so it should be either a read request, write request. So first thing you do is you acquire the IDE lock. That's mutual exclusion. The next thing you do is you append the buffer to the IDE queue. So IDE queue is some shared structure, it's a global variable, and you just append the block to the IDE queue. You append it to the end of the IDE queue because it's a FIFO, so you append it to the end of the IDE queue. So you just iterate over the IDE queue till you reach the end, and then you append to the IDE queue, right. So just now in this figure, just go till the end and then put your new buffer here. All right. Finally, we check if IDEQ is equal to B. So B is the buffer that was the argument to this function. So this is the buffer that I want to read or write. If IDEQ is equal to B, is checking what? If I am the first element in this queue, that's what it means, right? If I am the first element in this queue, then start the disk, right? So basically it means that the queue was actually empty right now, and this is the first request that's been made to the disk. So the disk is actually not spinning right now, it's not working right now. So I need to start the disk. So there's this function called ID start that's going to use in and out instructions to basically tell the disk to start. There's some standard which is basically telling it to start. So this disk has been started. If I am not the first element in the queue, then I don't need to start it. It's already started, right? And if it's already started, it will, as you're going to see, it will basically it's just serving one request, and as soon as it's done serving that request, it will pick the next request in the queue, and so on, right? So I don't need to do anything. If it's already started, it knows what to do next. As long as I've appended something to the queue, I'm fine. All right. Okay, and then I keep waiting on this condition. The condition is that whatever I wanted to do, read or write, if it has happened, till it has not happened, keep sleeping, right? The mutex is IDE lock, and the channel is the buffer on which you wanted to do this operation. Okay, all right. Let's look at, maybe it will become clearer if we look at what happens if the disk finishes. So when the disk finishes, the IDE interrupt function gets called, the interrupt handler, and what it's going to do is it's going to again acquire the IDE lock, right? Once again, so the interrupt handler, so the disk is finished, it has called the IDE interrupt handler, it will acquire the IDE lock, and it will check if the IDEQ is now, if the IDEQ is null. That basically means I don't know why I got this interrupt. It's possible that a device creates a spurious interrupt, so I just say it's a spurious interrupt, don't worry about it. And usually if I got an interrupt from the disk, it basically means that there must have been something in my IDEQ, right? That's why I was working and that's why I generated the interrupt. But if the device for some reason generated a bad interrupt, I should tolerate it, so the programmer is tolerating it. Otherwise you basically say that whatever was at the top of the queue has been addressed, has been serviced. So you basically move the top of the queue to its next. You read the data using the in instruction from the disk into the buffer's data, b.data. Okay, and so B is the top of the queue, right? So you are serving the top of the queue. You read the data into the B's buffer. You set its flags to say that now it's valid, or it's not dirty anymore, depending on whether it's a read or write request, and then you call wake up on B, right? Why do you call wake up on B? Because the process who made this request must be sleeping on B. So now you call wake up on B, so that's how you basically coordinate between a process who made the request and the disk who completed the request for that particular process. Okay, all right. And finally, if the queue is still not empty, which means there are more requests to do, then you restart the device for the next buffer. Okay, all right. So details aside, I mean, let's forget about how exactly the disk is being, what's the interface, what does in-SL mean, and how does ID start work. These are all sort of very too much detail that we don't really need. But what's important is how is synchronization happening, right? So there's a process who appends something to the queue, goes to sleep on the buffer that he wanted to actually read or write. The disk, when it goes to sleep, it also releases the IDE lock. The disk, when it finishes, generates an interrupt. The interrupt handler also needs to acquire the IDE lock because it needs to manipulate the IDE queue. For example, it will move the top of the IDE queue to its next pointer, right? So it will operate on the IDE queue, so it needs to take the lock, and then it calls wake up on any process that was waiting on that ID queue. So basically wake up makes it runnable, and so that process can now return from wherever it was. Okay, good. So what if a disk generates an interrupt so before that, what if a disk generates an interrupt while I was somewhere here? And so I started the disk, and before I go to sleep, the disk has finished. So let's say the disk is really fast, it just finishes immediately. Right?
You have acquired the lock, so interrupt handler cannot be invoked.
Right. So basically, because I have acquired the ID lock, interrupts are disabled at this point. This is a great example to understand why we need to disable the interrupts when we are holding a lock. Right? If we didn't disable interrupts, the interrupt handler could have run here and bad things could have happened. Because I'm holding the ID lock, this entire region, the interrupts are disabled. Interrupts get re-enabled only when you sleep and you release the lock, consequently. Right? So this entire region, the interrupts are disabled. Right? So there's no, so if an interrupt occurs, what happens is that the interrupt gets buffered by the hardware, and as soon as you re-enable the interrupts, the hardware basically gives that interrupt to you.
But that buffer is very small.
That buffer is very small, you know, 1 or 2 interrupts, it's okay. Right? You know, you're probably worrying about the situation. What if the interrupt gets lost and no future interrupt comes? I think we have discussed this before. So let's say, you know, usually the protocol is that if a device makes an interrupt, it expects for an acknowledgement from the CPU. So if it hasn't received the acknowledgement, we'll retry the interrupt. So there's you know, that kind of a protocol going on. Okay. All right. So so if an interrupt occurs here, no problem. Interrupt will be served only as soon as the ID lock gets released, and so the interrupts get re-enabled. The ID interrupt, when it gets to run, will try to acquire the ID lock. You can be sure that if it was only one CPU, then it will get the ID lock. Right? The only reason that that the interrupt handler may not get the ID lock is because another CPU is holding it, but the same CPU couldn't be holding this ID lock, because after all the interrupt got to run, right? So the interrupt got to run, that CPU couldn't have been holding the ID lock. If it was holding, then interrupts would have been disabled. So the whole reason, the whole point, the whole fact that the interrupt handler got to run means that the CPU was not holding any lock. So you know, you will that basically means that you will eventually get ID lock. So there's no deadlock problem here, right? And then you will perform this operation, and then you will wake up the particular process. When you call wake up, that process may not necessarily run immediately. Let's say it was a uniprocessor system, this interrupt handler is running. So you know, how can that process run? You have also disabled interrupts completely here. But when you release the ID lock and then you return from the interrupts get enabled again, and you know, because you have woken it up, it has become runnable. Whenever the scheduler gets to run next, it's going to get picked up and it can now proceed. Right? So let's say the process wakes up from sleep, it checks the condition again. This time it finds it to be true, false, and no, it can go on its way. All right. Notice that here inside the loop, when I'm saying while some condition sleep on this, I have not really checked for p dot killed, right? I said that usually when you come out of sleep, you should now, because you are doing this thing that any sleeping process will be made runnable. Is it incorrect to not check for sleep dot p dot killed, right? Well, I mean, it doesn't matter if it's going to check the condition. Even if the process was killed, you still want that the buffer has been read, the lock has been released, and now you can go on and check later, right? So so it's okay in this case. So it's not necessary that every sleep loop needs to have the killed condition killed check. You know, some need, some don't, for example, and one has to reason carefully about what needs it and what doesn't.
So why don't we need it in this case?
So one way to think about it is that eventually it's going to come out, right? So it's not a very long time that it's going to stay there. Now I'm not waiting for some child to exit, for example. I'm just waiting for the disk to finish. Right? So it's better to let it finish and then release the ID lock, and then basically let its caller call. So let the things be in a more consistent state. You know, I don't know whether the caller is leaving things in an inconsistent state or not. So you know, let it reach some boundary. This may not be the right boundary. This may be the innermost sort of thing, and if I just sort of start returning -1 from here, that may not be the right thing to do. So just an example. Sometimes you may want to check it, sometimes you may not want to check it. But the thing is that within a limited time frame, you should basically be exiting that particular process. Okay. All right. Here's another example. This example is also another an interesting illustration of why recursive locks are a bad idea. Right. So recursive locks are a bad idea here. Why? Because notice that mutual exclusion is required between the thread and the interrupt handler, right? And the mutual exclusion is being done using the IDE lock. Instead of making IDE lock like the way it is, if I made the IDE lock recursive, and the interrupt handler was actually able to get the IDE lock also, then bad things can happen, because you can take a lock, you could be in the middle of something, and now when the interrupt handler gets called, now it takes the IDE lock, and so it assumes some invariants which are not guaranteed to be true, right? So recursive locks, especially in presence of interrupts, are definitely a bad idea. In general, also, it encourages bugs, but if you're providing mutual exclusion with respect to interrupts, then recursive locks are a bad idea. All right. Okay. Also, because I have, I'm holding a lock, I'm trying to acquire IDE lock, I need to basically ensure that there is some kind of ordering. So any caller, if it's possible that the caller is also holding certain locks, so this IDE lock needs to be ordered with respect to whatever locks the caller is holding. So one invariant it could be that the IDE lock will always be the innermost lock. You will never hold IDE lock and then try to acquire another lock, so that way you can prevent deadlocks, right? So you have to worry about these things also. So another example of why locking and modularity don't gel, because here you have to worry about, okay, so I'm taking IDE lock here, I shouldn't be taking IDE lock somewhere else where it's possible that you take the IDE lock and try to take IDE lock somewhere, another lock after that. Okay, good. So with that, I think we have done a lot of synchronization, and synchronization was by far one of the most sort of important and practical topics in programming in general and in operating systems. Now I'm going to talk about demand paging. All right. So we know that we've looked at virtual memory, and we saw virtual memory using segmentation, where there was a base and a limit. We also saw virtual memory using paging, and we said paging is more flexible, although paging has more overhead, because you have lots of page size. You need to maintain a page table, and so but we said then there is a cache called TLB, right? So there is a TLB that caches page table mappings. And assuming that this cache has a very high hit rate, and this cache is very fast, and by fast I mean it's sub nanosecond. So and the time it takes to actually dereference the TLB is roughly equivalent to the time it takes to dereference a register, right? If it's that fast, then paging makes a lot of practical sense. And so hardware developers have so TLBs actually work in practice, because usually programs have a lot of locality, lot of spatial and temporal locality, which means that the same locations are likely to be accessed over and over again. Also, if you access a location, then very likely you're going to access locations close to that. So because programs exhibit a lot of spatial and temporal locality, the hit rates of TLB caches are usually very high, and on the order of 99.9% or something. And so you basically do not pay the cost of paging, that, right? So the cost of paging was basically this dereference of page table, which is costly. So but that gets eliminated because of TLB cache. And so usually so here is how your memory will look like. So let's say this is the physical address space, and these are multiple virtual address spaces. Let me draw this with a different color. let's say this is GCC, and this is let's say VI, and so on, this is browser. Then some page is going, the pages are strewn across like this in the physical address space, right? And these lines are page sized. Okay, so we understand all this. Now in the simple world that we have discussed so far, we said that whenever you load a program, the entire memory of that program, the executable and whatever other data it needs, is basically loaded from the disk into the physical memory at load time, right. So basically initially the program lives on disk, let's say GCC and VI, including its code and data, and as soon as you load it, we said that the entire, there's in some format called a.out with the executable, and so the a.out format is parsed, and the loader basically creates an address space, allocates pages in the physical address space, creates an address space, and loads the entire contents of the executable into physical memory. All right. It's quite possible that the process was just started to just stop immediately, or it's not going to access all the memory that it actually has in the executable, so it's going to access only a fraction of the memory that's going to do it. So it doesn't make sense to actually pull all the things at once, and so what you can do is you can pull things from disk on demand, and that's what's called demand paging, right. So the idea is that whatever you basically at load time, you just create an address space, all right. So let's say this is an address space, this is the virtual address space, and let's say this is the physical address space, and let's say this is the disk. Then you have created the address space, let's say these slots are pages, so some of these pages are currently mapped inside your physical address space, and the others are not currently loaded and are actually pointing to the disk at some disk block, right. So it's not actually a loaded, so the page is not loaded immediately, but in the page tables you have stored this information that this page corresponds to this particular disk block, all right. So and you say that it's not present, right. So this particular page is not present, so the present bit is off in the page table, and you have stored this information that this particular page actually lives on the disk at this particular offset. So when you run this process, you are going to if you don't touch this page and you exit, you have saved a lot of work. If you touch this page, then you basically take an exception, right. An exception happens because you try to access a page that's not present, right, and so this exception is called a page fault. If you try to access a virtual address that's not currently mapped in the page table, or it's not currently present in the page table, you take an exception, that's called a page fault. The page fault will cause the operating system to run, the operating system's page fault handler to run on the kernel stack of that particular process. And in the previous discussion you were saying that this the page fault handler may want to kill the process, or it may want to send a signal to the process depending on whether the operating system implements signals or not. But in this case he may want to do one more thing, which is to check if this page is actually mapped to a disk location, and if so, it shouldn't do any of these, it shouldn't kill the process. In fact, this is the operating system playing tricks under the carpet. The process was actually doing everything in good intentions, it's the operating system that's playing tricks under the carpet. So what it should do is it should allocate a page here, let's say it allocates a page here, loads from the disk block to here, marks this present, and creates a mapping like this, right. So that's called demand paging. And demand paging is a very sort of useful optimization, because for the common case you don't need, all parts of the executable are not going to get accessed, only some parts of it are going to get accessed, and so you save a lot of disk reads, right. And also you reduce the pressure on your memory, you don't need to allocate that many pages on your memory, so there's more free memory available on your system, right. In general, your system may be running only on a small amount of memory, let's say your system is running on 512 megabytes of memory, yet your operating system will allow you to load larger processes. So for example, your operating system will allow you to load, gigabyte size process on a machine of size 512 MB. It's done because of the demand paging running underneath the covers, right? Yeah.
A page fault occurs and we load the missing page into the pageable. Now we want to rerun the command which caused the page fault.
Okay, yeah, good question. We want to discuss it very soon. So basically, there's some instruction that tried to access that particular address, and so a page fault occurred. The operating system is going to get to run, and it's going to load the page, and now you will need to restart that instruction, all right? And so that's how it's run. Basically, you just restart that instruction. What you need to make sure is that if you run the instruction twice, or the first, if an instruction causes an exception, it doesn't cause any partial execution of its logic, right? So either the instruction completes successfully, or it doesn't do anything at all and causes an exception, all right? So this is a property of the hardware or the architecture, and this property is called precise exceptions. Right? So if an architecture supports precise exceptions, if there was an exception at an instruction, it is safe for the operating system to restart that instruction and basically assume that nothing happened in the previous execution of that instruction. All right. Okay. All right. So we'll continue this discussion next lecture.